Okay. So, can I start?
Yes, go please.
Okay. Okay. Hello everyone. This is Junzhou, and today I will present a paper about the word action model. And the title of the paper is Fast-WAM, Do word action model need test time future imagination? And the reason I chose this paper is because it studies a very important question in current word action model. That's the relationship between the future imagination, the future prediction, and the action generation. So first I like to clarify three related concepts: VOA and WM and WM. And for the first VOA stands for the Vision Language Action Model, and is a kind of robot policy learning model for the robot control. And so you can see the left figure. It takes the current visual observation and the user language instruction as inputs, and it directly outputs the robot actions. And for the one model, it's a kind of predictive model. So you can see it also takes the current visual observation and the action as inputs, and it predicts the future observation, the future state of this environment. So you can see that compare with the VOA, the one model does not try to answer the question like what should I do under this language instruction, but tries to answer the question like what will happen if I do this action. So and for third one is the word action model. So you can see actually what action model is a combination of VOA and the word model. So you can find that it also takes the current visual observation and the language instruction as input, and this model tries to model the future prediction and the action generation together. And this kind of model uh, tries to utilize the future prediction to to guide the action generation. Because during the future prediction process, the model can capture some capabilities like the physical dynamics, the temporal influence of this environment, which is very important and helpful for the robot action generation. So it's a basic concepts of these keywords. And next, let's see how existing word action models work. So most of them follow a paradigm of imaging then execute paradigm. Uh, the idea is uh, um, the idea is intuitive. I mean, um, if a robot wants to execute an action, and the model will first imagine what the future looks like, and takes this future observation into consideration and generate more reliable, more reasonable actions, just like humans. And in this figure, there are two representative word action model paradigms. In column A, it's a joint word action model. So you can see this model, this paradigm one tries to predict the future observation and the action generation together in a shared generative process like diffusion, denoising, like the autoregression. And the second one is a IDM style reduction model. Here, the IDM stands for the inverse dynamic modeling. And this paradigm is a two-stage model. And in the first stage, the model tries to predict the future observation first. And in the second stage, the action expert um, generates the final actions based on this predicted future observation. So, so you can see both designs explicitly imagine future observation at the test time. In some way, it's easy to understand, it's easy to follow, but it also has high computational cost and will increase the latency. I mean, when you apply it into a real robot control, because the future observation generation is this interactive process like denoising, like auto regression. Is very time consuming for the real robot control. So that means the the efficiency in current word action model is very problematic. So that's now the above analysis. The key research question of this paper is very straightforward. Do word action models really need to imagine future observation at the test time? And to explore this question, this paper has two hypotheses. And in the first hypothesis is future generation provides extra foresight during the inference, which under this hypothesis, which means explicitly imagining the future observation is very important. If we skip it, it will cause a large performance drop. And for the hypothesis B, video modeling many shapes better the latent word representation during the training. Under this hypothesis, the model can benefit from learning to predict the future observation during the training, because this training objective can force the model to learn to understand the environment, like the object motion, like the interaction and the physical dynamics. But during the inference, this model may not need to explicitly generate the future observation, the future video frame. So to verify these two hypotheses, the core idea of this paper is to keep the video co-training during training, but skip the future video generation during the inference. And just illustrated in column C, is a very simple but effective solution. So you can see during the training, the model still learns to predict this future observation and the action together. But during the inference, it only utilizes the current observation F0 to generate the final actions, which means the video generator model here becomes a single pass word encoder to generate the latent word representation, not a test time future video generator. So In this way, it keeps the training benefit of the word modeling, but avoid the test time generation cost. And here is the detailed architecture of this model. So you can see the model utilizes a video DIT as a word representation learning backbone, and action DIT as action expert to generate this action trunk. And it's a kind of MOT architecture, so which means the video branch and the action branch can communicate with each other with shared attention. And also for the language encoding, it utilizes the cross attention to attend each this two branch. And during the training, the video branch and the action branch means the feature observation and the action generation will be optimized using standard flow matching loss functions. And during the inference, the video generation branch will be removed, and only the current frame, the first frame, the latent tokens are used to generate the latent word representation feature for the subsequent action generation. And also on the right side, it shows the attention mask during the training and the inference. So you can see for these two branch, the video branch and the action branch, it utilizes a bidirectional attention scheme inside. And for the action branch, it cannot see the future video frames. It's a kind of causal attention mask because I mean in real robot control, the current action cannot see the future or future state, future observation, and it's a constraint. So, so to verify the above hypothesis and the author's claim, for the experiment, here is the experimental design, and this paper compares four variants to test whether the performance comes from the training time video modeling or the test time feature imagination. So which means if test time feature generation is a key factor, and then the fast reduction model should be much worse than the joint the IDM variants. And if video co-training is a key factor, then removing this co-training scheme should hurt the performance a lot. So here is the four variants. The first is the proposed method, the regular model, and it utilizes the video co-training during training, and but not explicitly generated the future frames during the inference. And for the joint version, it represents the joint word action model paradigm, and it utilizes the video co-training, but at inference, the future observation and action token are generated together. And also for the IDM version, it represents the IDM style word action model paradigm, and it first generates the future observation and then predicts the final actions. And the first one is a model without video co-training. This removes the video modeling objective during the training, but keeps the inference style. Okay, for the model evaluation, this paper also utilize two simulated benchmarks and one real-world tau folding task benchmark for the model evaluation. So here is the main results on the robot twin benchmark. So you can see the regular model achieves comparable performance compared to this embodied pre-training model, and also can outperform joint and IDM version variants. And also you can see the model without video co-training, the performance will has a significant performance drop. So from these results, it indicates that explicit test time feature generation is not as a dominant factor, but as video co-training is much more important. And here is another benchmark evaluation. Also, the results trend is the same with the last benchmark. So you can see also the regular model can achieve comparable performance with this embodied pre-training method and has a closed performance with this joint and IDM variants. And also for the model without video co-training, and the performance significantly drops. And this results supports the claim that video modeling is valuable mainly as a training signal. And here is the real world task results, and the metric contains the success rate, the grasping object success rate, and the latency of the whole system. So you can see the regular model runs at 190 ms, while the IDM version takes 800 ms. So these results also show that the video co-training variants are much better than no video co-training variants. And also, the Fast-WAM model is most efficient variant. That means the Fast-WAM model is much more suitable for the real-time robot manipulation task. Okay, here is the conclusion. So from the experimental results, we can conclude that first, the video co-training is very important across both simulation benchmark and the real-world benchmark. Removing video co-training will cause a clear performance drop. And second, the future prediction can be useful as a training signal. Even if the model does not generate the future observation at the test time, the video prediction objective can help learn a better word or action representations. And the third is skipping explicit future observation can improve the efficiency. This is especially important for real-world robot control, where the latency directly affects the execution process. So in general, in my world, the main takeaway is that this work changes how we understand the future, how we understand the future generation in current world models, and the future prediction may not need to be explicitly generated during the inference, but it can refer as training time supervision to learn a better latent word representation. Okay, so that's all my today's presentation. Thank you very much.